we know that when an object travels in a circle, it takes a force to push that thing around the circle to keep it accelerating centripetally. Now, what I want to look at in this lesson is what happens when you go around a corner in your car. And we're going to just keep this video to flat curves. So we're not going to look at things that are banked up at an angle. We're just going to leave these things flat. So from a top-down view, here's my highway. It starts to curve like that. And even though it's not a complete circle, we still have a radius of curvature. So even though you're not going all the way around in a circle, we still treat this as centripetal motion. It still is acceleration towards the center. So you have some radius r where that curve is from, and you are in your vehicle and you're turning around this corner. So this top-down view, there's your car. Now, from a side view, there are a couple forces acting on that car. Your car is on the ground. And so we've got a force due to gravity pulling it down and the normal force from the ground pushing up on it. And those two forces balance on a flat level surface. The sum of the forces in y is 0, and that tells us the normal force will equal mg. Now, there's one more force on this. On this picture, it's directed towards the center. We're going to call that Ff for F friction. Friction is the only thing that can apply that force, and it is this way. And it is static friction. Now let's think about why. Okay, if you are navigating around the corner like this, your car and you have your inertia, and so a second earlier you were going this way, and your inertia wants to keep you moving that way. But you turn the tires, and so the pavement is able to push you around this curve. And you feel like it's an outward force, right? Because you feel like the side of your car, your seat, is pushing you in towards the center. So you feel like there's an outward force on you. But there's not. That's just you trying to keep yourself moving, your inertia trying to keep you moving in a straight line. So there's a force in on the center. Now, remember, friction opposes motion or intended motion. And so the car, its inertia wants to keep it going in a straight line, but friction opposes that and pushes it in towards the center, causing you to turn in a circle. Which means, based off of this, we can figure out the maximum speed you can turn a corner based on the coefficient of static friction. So if this coefficient of static friction is mu s, and by the way, the fact that this is static friction is really, really important because it opposes the intended motion. Kinetic friction opposes motion. And so if this is static, and it is static because at any instant your tires are not slipping, they are rolling across the ground. So this is not sliding. If this is your tire on the pavement, this is not sliding backwards or forwards or into or out of this board. Rather, the next little section of tire is going to roll down and this is going to roll up. So it is instantaneously at rest with the ground. It is not sliding. But if this switches to sliding friction, if you hit your brakes and lock up your tires or you lose traction, and this goes from static friction to kinetic friction is only going to oppose your velocity. So if you happen to be moving this way, kinetic friction is going to go against that. And so you're going to actually continue moving in this way. You're just going to get slower, which means you're going to drift across traffic and out across and into the next lane and then off of the road. Okay, so keeping it static friction is important. Kinetic friction will not let you turn that corner. Kinetic friction will just slow you down as you move in a straight line. So, back to this. Maximum speed I can navigate this corner. I can figure it out if I know the radius and I know the coefficient of static friction. Or let's just say the radius is r and the coefficient of static friction is mu s. Well then, the forces that are acting on me, I've got the normal force and gravity, which will add up to 0, and I've got the static frictional force, which is actually supplying the force needed to turn the corner. So the net force is the static frictional force, which is mv squared over r. Right? That's Newton's second law, but the only acceleration is centripetal acceleration, which is v squared over r. Well, Fs is Fn mu s, and Fn in the horizontal flat case is mg. So I have mg mu s equals mv squared over r, and mass is on both sides of that equation, so it can cancel out, and I can multiply both sides of my equation by r, so I get r times g times the coefficient of static friction is equal to velocity squared, so I can square root both sides, and there it is, an expression that will tell me the fastest speed I can navigate a corner on a flat surface. Okay. Lots of times on highways, you'll see the little yellow signs when you're going around a corner that tells you, hey, slow down. You've got, the speed limit on this road is 55, but you're only supposed to take this road at 35. They are doing that because they know the maximum speed and they're reducing that speed to keep you safe. And in icy and wet conditions, you need to slow that down even more because your coefficient of friction will be less. And if you go from static to kinetic, you're no longer navigating that corner, you are sliding through it. Okay. Now, another cool way you can use this physics is actually, let's say you wanted to know the radius of a curve on a flat highway. You can figure it out based on your speed and one measurement. So, when I was in high school, on my rearview mirror, I had some fuzzy dice that would hang down. Now, as long as I was traveling in a straight line at a constant speed, those little fuzzy dice would hang straight down. But if I'm turning a corner, they swing to the outside of the corner. And let's think about why, right? If I'm turning a corner, these swing outside towards the outside of that corner, so I'd be turning to the right here. Well, that's because these things have to have some force on them that's going to cause them to accelerate centripetally towards the center of the circle, which is this way. And the only thing that's exerting a force on this, besides gravity, is the tension in the string. So the string is going to pull up and right against gravity, which is pulling down. So as soon as I started turning a corner, there was more tension in the string trying to pull these things straight. And so there was this force and this force, the two components of tension. So if I measure this angle, I can actually figure out the radius of curvature of the circle if I know how fast I'm going, which my speedometer will tell me, right? So let's look at that example. So if that is the angle theta between vertical and where these things swing out to, and the radius is given by r, the angle is the angle, and my speed is v. How are these things related? How can I figure out what the radius of curvature is? If I know two of these three things, how can I figure out the third? Well, let's look at these forces in a little bit more detail. I've got my object that is swung away from vertical. The forces that are acting on it are gravity and tension. And tension has components. Tension has a component that is pulling in, Ftx, and a tension component that is pulling up, Fty. And this angle theta would be the same as the angle from vertical right there. And so the net force acting in the x direction is causing it to accelerate around the curve, which is equal to mv squared over r. The net force in the y direction is equal to Fty minus Fg, which equals 0, because it is not accelerating up or down as we navigate this flat corner. And so Fx is really Ft, and this is Ft right here in the string, so that means I've got Ft and x is opposite that, so Ft sine theta equals mv squared over r. Well, I don't know Ft, and I don't know r, that's two unknowns. But I can go to my y direction and I can say Fty, which equals Ft, and that's adjacent, so cosine theta equals Fg, but Fg is mg. So now I can say Ft equals mg divided by the cosine of theta, and I can plug that in to this equation right here. So instead of Ft sine theta, I'm going to say mg divided by cosine theta times sine theta. So I have mg divided by cosine theta, I'm plugging that in for Ft, times sine theta, that's sine theta over 1, equals mv squared over r. And now I can see the masses on both sides, it'll cancel out. G times sine theta divided by cosine theta is g tangent theta equals v squared over r. Which means I can solve this for r, I can solve it for v, I can do whatever I need to, but I've got a relationship now that includes only the angle, the velocity, the radius, and g, and so that can help me figure out if I knew the speed and I knew the angle, what the radius of that curve was.